Welcome to the Universal Gravitation video. You should have a homework sheet and be prepared to take notes in your spiral notebook. The history of astronomy started with the ancient Greeks. A philosopher by the name of Ptolemy is given credit for the idea of a geocentric universe, which means Earth is at the center and everything revolves around the Earth. In the 1500s, a Polish cleric by the name of Copernicus proposed a heliocentric solar system. Helios is the sun, so it's a sun-centered solar system. He didn't get a lot of credit back then because people didn't believe him, because they felt that there was no way that could be true, because if the Earth was moving so fast around the sun, why couldn't we feel it? Well, of course, Copernicus didn't know about things like inertia back then. A little later, Galileo was convinced that Copernicus was correct because he was observing the sun and Venus and the moons of Jupiter with his newly invented telescope. Another guy by the name of Tycho Brahe in the late 1500s made a whole bunch of measurements of planetary motion to support his own views of the solar system. And then, a few years later, in the early 1600s, a man by the name of Johannes Kepler used Tycho Brahe's data to come up with some special laws, which we call Kepler's laws. You don't need to know what they are, but they explained very precisely how the planets moved. The problem is they didn't explain why they moved the way they did. Well, along came Isaac Newton in 1666. This is about 45 years after Kepler. And he reasoned that the moon is falling for the same reason that an apple falls. They're both being pulled by the Earth's gravity, and so the gravity must reach all the way up to the moon. So he mentioned that the moon was falling, and if we look at Newton's first law, we know that an object is in motion, and it will remain in motion unless it's acted on by an outside force. So the outside force is gravity. If we take a look at this cannon right here, we can see that if we shoot the cannonball and it doesn't have enough force, it follows a parabolic trajectory and hits the ground. If we shoot it a little harder, it follows a trajectory and hits the ground a little further away. And if we shoot it really hard, it goes a really far distance and hits the Earth really, really far away. But eventually, if we shoot it really hard enough, it stays in a circle and comes back to where it started. Well, we call that an orbit. And so it will continue to orbit around the Earth forever, and that's what the moon does. It's continually falling around the Earth. Now, Newton came up with something called the law of universal gravitation, which means that every object in the universe is attracting to every other object. And they are attracted along a line between the centers of those two objects. The force is proportional to, that's what this symbol right down here means, the product of the masses, meaning mass 1 times mass 2, and it's inversely proportional to the distance that separates their centers squared. You have to remember to square this. So it's proportional to the product of the masses and inversely proportional to the square of the distance between them. Now notice that force on 1 and the force on 2 are the same, because we know from Newton's third law, for every action there's an equal and opposite reaction. So one attracts the other, and the second one attracts the first one. Now the problem with this was that all we knew was that they were proportional to each other, but we didn't know what that proportionality constant was. Well, along comes a guy by the name of Henry Cavendish in 1798, and he used a contraption that used a couple of small masses and a couple of large masses. And what happened was the small masses were attracted to the large masses, and it caused them to rotate on a wire. And Cavendish observed how the wire twisted with a lot of fancy equipment, and he used it to measure the force of the small ball attracted to the large one. And with that force now known, he could calculate something called G, which has come to be known as the universal gravitational constant, which is the same everywhere in the universe, even though gravity isn't. The universal gravitational constant is the constant of proportionality in the equation that we just saw. The magnitude is the force exerted by two 1 kilogram masses apart. The constant here is 6.67 times 10 to the negative 11, and the units are newtons times meters squared per kilogram squared. And you'll see how that works out if you cancel your units in any of the equations. Now, I mentioned that the force of gravity is proportional to the product of the masses and inversely proportional to the distance squared. Well, that's because gravity behaves like light. Let's take a look at this light bulb in the center of these three rings. The light shines out, and when it hits the first ring here, let's just draw a square, and you can see how bright the light is. Now, if we double the distance, the square is now twice the width, but it's also twice the height. So 2 times 2 is 4. If we triple the distance, it's 3 times as wide, but also 3 times as high. So 3 times 3 is, of course, 9. So what that means is, as we increase our distance, the strength of the light is dimming proportional to the distance squared, or inversely proportional to the distance squared. So we have 1, then we have 1 over 2 squared, then we have 1 over 3 squared, and so on. It spreads out and gets dimmer. Well, gravity spreads out and gets weaker. So if we double the distance, we have 1/4 of the strength of gravity. Now, gravity and orbits are intimately related. We just learned about centripetal acceleration, and we learned that the acceleration is equal to the velocity squared divided by the radius. We also learned that the centripetal force is equal to the mass times the acceleration. And lastly, we learned that the force in circular motion is directed towards the center, and that's called centripetal force. Well, guess what? The centripetal force in an orbit is gravity. So when we spin the stopper around on a string, the centripetal force is caused by the string. The moon spinning around the Earth, the string is gravity. So the centripetal force and the gravitational force between the Earth and the moon are exactly the same thing. So in review, objects orbiting around the Earth are actually falling, but they have enough velocity to avoid hitting the Earth, and so they keep on going around and around. It's just like the stopper spinning around on a string. Gravity is the string. Everything pulls on everything else with a force that depends on the masses of the objects, and it's inversely proportional to the distance between them squared. So gravitation decreases according to something called the inverse square law. And that applies, as you'll find out later, to light, to electric charge, to magnetic fields, and a lot of things. So you need to learn that inverse square law. So now let's look at your homework problems. Your homework problem number 1 on your worksheet. I'm going to do 3 of them for you. First of all, how much would a 70 kilogram person weigh on Mercury? We're going to use the guess method, so I've written down GUESS over here on the side. First, let's list what we know. Well, M1 is the mass of the person, 70 kilograms. Well, they're standing on Mercury, so M2, we need to know the mass of Mercury, 3.32 times 10 to the 23rd kilograms. That number is right up on the top of your worksheet. The distance to the center of Mercury, if you're standing on the surface, is just the radius of Mercury, and that's 2.44 times 10 to the 6 meters. That's the distance to the center, from your belly button to the center of Mercury. Our unknown is the force of gravity on Mercury, which is, of course, the weight on Mercury. Remember that the force of gravity on an object is its weight. The equation we're going to use, the force of gravity is equal to G, that's big G, not little g, big G, times m1 times m2 divided by the distance squared. We don't have to rearrange this equation, we just need to substitute. And when we do, we get this big monster. It's really just big because there are a lot of units in there, which you don't put in your calculator. But you have 6.67 times 10 to the negative 11. Remember, you put that in with the EE button, 6.67 EE 10, and then your sign change 11. These numbers are on top, so times 70, and then times 3.32 EE 10, or EE to the 23. So 3.32 times 10 to the 23. And then on the bottom we have divided by 2.44 times 10 to the 6th. And remember that it is squared. Don't forget that. You need to plug this into your own calculator to make sure that you get the same number I do. A lot of people are getting wrong answers because they're either putting them in their calculator wrong, or for some reason their calculator thinks it's smarter than they are. But you should practice this yourself to make sure you're getting the same numbers. Just because you can write it down doesn't mean you're going to get the same answer. The answer here is 260 point newtons. I put the decimal point in there to show that there are 3 significant figures like there are in all the numbers that we have been given in our guess method. So let's look at problem number 2. If Pete, who has a mass of 90 kilograms, weighs himself and finds that he weighs 135 newtons, how far away from the surface of the Earth is he? Well, he's standing on a super tall building, a bunch of miles high probably, because we know that from our old equations, force weight is equal to mg. Well, 9.8 or 10 times 90 kilograms, he should weigh about 900 newtons, but he only weighs 135. So he's got to be really far away. Let's figure out what we know. We know that he weighs, or has a mass of 90 kilograms, and that he weighs 135 newtons. The mass of the Earth is 5.98 times 10 to the 24th kilograms. What we're looking for here is the distance. So we need an equation. Well, we're going to use the same equation in all of these. But the problem is, distance is on the bottom over here instead of where we'd like it on the left side of the equal sign. So we're going to have to rearrange this equation, something you'd better get good at. The distance was squared, so after we rearrange, we're going to have to take the square root. And we end up with the square root of big G times the 2 masses divided by the force of gravity. And when we substitute that in, again, we got a really big looking thing here, but we've got square root, so we have to hit that square root button, and it's going to open the parentheses for them, and we're not going to close till we're done. I put parentheses here to show you how these numbers separate, but don't you close your parentheses until we're done with these numbers. We have 6.67 times 10 to the negative 11. Remember, you put that in, 6.67 EE, sign change 11. Then we're going to say times 90, and then we're going to say times 5.98 EE 24. Then we're going to divide by 135, and then we're going to close our parentheses. That is so that everything is under the square root. When you're done with that, you go on and hit the enter button, and you should get 1.63 times 10 to the 7 meters. If you didn't get that, you're putting something into your calculator wrong. Lastly, we're going to work on problem number 3. Captain Kirk, who has a mass of 80 kilograms, beams down to a planet that has the same radius as Uranus and finds that he weighs 1,250 newtons. What's the mass of the planet? So our givens are Captain Kirk's mass, 80 kilograms, the force of gravity on this planet, which is 1,250 newtons. Now that's his weight on that planet. And the distance to the center of the planet from the surface is its radius. And since we know that it's the same as Uranus, we can look that up on the table at the top of the the mass of the planet. So the equation we're going to use is this one right here, and we need to rearrange it for M2. So we do that magically, and we get M2 is equal to the force of gravity times the distance to the center squared, divided by G, and divided by M1, Captain Kirk's mass. We substitute all of this in, and we have 1250 times 2.61 times 10 to the 7 meters, and then don't forget to square that. We're going to divide by 6.67, and remember to hit the second EE button, sign change, 11. And now look at this guy, 80 kilograms on the bottom. Do you think we times it? No. Divide by, it's on the bottom. If you multiply, you're going to get the wrong answer. Divide by 80, since it's on the bottom, and when you're all done, you should get 1.60 times 10 to the 26 kilograms. If you got a number that's a whole lot bigger than that, then you multiplied by 80 instead of divide. Remember, if it's on the bottom, hit the divide button.